In a previous video, I had introduced you to the concept of ionization energy. We defined it as the amount of energy required to liberate an electron from an atom, or a gaseous atom to be precise. Now, it turns out that the ionization energies of elements give us a good way of describing whether or not those elements are metallic. So in this video, we're going to look at this relationship between ionization energy and the metallic nature of different elements. So let's get started. Our formal objective, in this video we only have one objective, is to understand the relationship, just like I said, between the ionization energy and the metallic nature of objects. In order to answer this, our first question is, what exactly is a metal? The definition is quite simple. We define a metal as an element that readily forms positive ions, or cations. How do you form a positive ion? By losing an electron, by losing a negative charge, losing a negative vibe. And like I always say, to remember that cation is positive, you can think that the T there looks like a plus sign. So now if we look at this picture, what is this picture showing us? It's showing us how easy it is to remove electrons. The first ionization energy is how easy it is to remove an electron from these atoms. What would be your guess about the relationship between this and the metallic nature? Well, here it is quite simply, is that a low ionization energy means that that element or atom will easily form cations. Why? Because the low ionization energy means it has a low barrier to pulling off the electron. We don't need to put in a lot of work to pull off an electron. So if we can easily pull off electrons from these guys, then they must easily form cations, and these must be then the famous metals. Let's look at a quick example here. Here we have lithium, a neutral lithium atom with a nucleus here which has 3 protons as indicated by its atomic number there, 3, and 3 electrons. Now if we add some amount of energy there, which we call the ionization energy for lithium, or the first ionization energy for lithium, we can liberate an electron and create a lithium positive ion there. And there's the amount of energy required to do that, 520 kilojoules per mole. Is this high or is this low? Well, let's look at it relative to fluorine. To remove an electron from fluorine, to create this fluorine positive ion, we need 1681 kilojoules per mole. So this ionization energy is much larger than that one. Therefore then, we categorize lithium as a metal because it's relatively easy to remove that electron. It takes some work, but it's relatively easy. Whereas for fluorine, it's quite difficult, and so we class that as a non-metal. As you can imagine, the boundary is kind of arbitrary, but we've defined this based on sort of a number of other properties, actually, not just first ionization energy. You kind of already understand this about metals. You understand that they easily lose electrons because you know about electricity conduction. Here we have a metal, and what a metal is what a metal solid is basically a sea of electrons. We have these liberated electrons in a lattice or an array of positive cations there. So because lithium doesn't hold on tightly to its electrons, when it joins with other lithium atoms, what tends to happen is those electrons just tend to kind of go willy-nilly, kind of hanging about wherever they like to hang out. Okay? And because of that then, because we have these free electrons, if we apply voltage, as we know, electricity is the flow of electrons through an array of metal cations. If we apply a voltage then, we can send electrons flowing, creating electricity. So it's because these guys, metals, have a low ionization energy, which means it's easy to remove their electrons, that these electrons tend to kind of already hang out outside of the atoms, right? At any sufficiently high temperature, we already have enough energy in sort of the ambient atmosphere to sort of liberate these electrons, okay? And therefore, if we apply a voltage, like I said, we can create an electric current. So you kind of already know this about metals, that they lose electrons easily. That is why they conduct electricity. Okay, so now we have again this picture, and like I said, we can use this to figure out what are metals, what are non-metals, or what are metalloids. Scientists have done this, and here is the resulting picture. So here we have the metals. In the middle, we have the staircase of metalloids, And then on the right side, we have the non-metals. Some important things are that most of the metals, or most elements of the periodic table, are metals. And that includes the lanthanoids and the actinoids. Remember that this is a condensed periodic table. We really have sort of 14 more groups here that are squished or removed from you. So the lanthanoids, all 14 of them, and all 14 of the actinoids are indeed metals. And you can remember the names of metals by realizing that many of them end in IUM or UM. So if I gave you, I don't know, vanadium, you would tell me that's a metal because it ends in IUM, or I don't know, gold. Gold is an exception. Mercury, actually mercury means, the Latin, Hg, is like hydrogargium or something. And so that's why it doesn't end in IUM, because the original Latin name did end in IUM. Or gold was originally aurum, so that ends in UM. So that's why you have some of those exceptions. Or Fe, iron doesn't end in UM, but the original Latin term, which is ferrum, ends in UM. Okay, that's by the way though. So now we understand what the metals are. What are the nonmetals? Nonmetals will be things that don't lose electrons easily, rather they gain electrons easily, these guys, or also the noble gases, which don't do anything with electrons. So basically anything that's not a metal is a non-metal. They're really defined by virtue of the fact that they are not the metals. And of course the metalloids is the staircase here. Okay, so you could draw the staircase. Although in this 3D picture, then everything looks like a staircase. Now I'm a bit lost. Where's the staircase? No, it needs to come down one, and then across like that. Okay, so above and below each step of the staircase, we have a metalloid, okay, with the exception here of aluminium. That's a very bad picture. Maybe I'll link you to a picture below to understand how to locate the metalloids. So now, generally speaking then, metallic behavior follows a diagonal trend, where we have the most metallic elements here and the least metallic on that side. I thought I had bitten my tongue there. And so generally, like I said, the lowest ionization energy will give you the most reactive metals. In this case, francium. Actually, there's some debate about whether cesium is more reactive than francium. I think cesium ends up being more reactive because of some relativistic reasons, but I think the IB considers francium to be the most metallic or most reactive metal. So we leave it there as francium. And on that end, the highest ionization energy, which is not a noble gas, would be fluorine, and that is the most reactive non-metal. So the noble gases have higher ionization energies, but they do not do any chemistry, so we do not care about them in terms of reactivity. So now we have the yellow light on this objective. Let's see if we can get the green light by getting some questions correctly. Here's one question for you. Which of the following is true about the element chlorine? Pause the video and think about how you would answer this question. It says that the first option is that it has a relatively high first IE, and it's a highly reactive metal. Relatively low first IE, and it's a non-reactive metal. Well, obviously we can cross those two out because those aren't going to be correct. It's not a metal, it's a non-metal, right? And then the question is, does it have a high or a low first IE? Well, you can look at your data booklet. So I've given you a section here of the data booklet, section 8. At the top left, you can see the first IE of each element. And we can see that chlorine here has a 1251 kilojoules per mole first IE. And you can see relative to many of the other ones here, most of these here and everything here, that's relatively high. So it has a relatively high first IE. And that makes it a highly reactive non-metal. So our answer there is, our answer there should be C. And there, I guess, is a clue that I should have given you before I gave you the answer. But there's your clue, and there's your answer of C. So we know it's highly reactive because you've probably seen signs like this for dangerous chlorine gas. Although I'm not sure, where would you have seen that? Maybe in a video game or something. Okay, here's another question for you. Of the 4 options shown, which is the most reactive metal? Again, pause the video and think about this one. How would you answer this one? Which is the most reactive metal of these 4? I'll show you a clue in a second. Here's the clue. Is the first ionization energies, and you should remember that reactivity tracks ionization energy. So low ionization energy gives you high reactivity for the metals. So the answer here, of course, should be what? Rubidium, right? Because rubidium here has the lowest ionization energy, and therefore it'll be most easy to pull off an electron. Let's do the last one. Of the 4 options shown, which is the most reactive non-metal? Pause the video, think about it. When you're sure of your answer, then you can unpause. Here's a clue. Again, our picture of the first IEs. And we say here that reactivity tracks ionization energy. For metals, low ionization energy equals high reactivity. That's not relevant to this question, so I shouldn't have put it there. Okay, so we care about those guys on that side, the non-metals. The answer, of course, should be fluorine. So we can see fluorine is the most reactive of these set. Cesium is not a non-metal, so we can cross it out. Helium is a noble gas. It doesn't do any chemistry, therefore it can't be highly reactive, so we cross it out. So we have nitrogen and fluorine as our options, and we remember that reactivity for the non-metals increases diagonally like that. So fluorine is more reactive than nitrogen. Generally speaking, the most reactive non-metals will be fluorine, oxygen, and then chlorine. Although based on what I've told you, you would expect maybe nitrogen will be more reactive than oxygen. And nothing is ever that simple in chemistry. We haven't talked yet about the electron affinity, which is really what you should focus on for the non-metals. But we'll talk about that in a future video. For now, though, I think we're done. We understand the relationship between IE and metallicity, if you like. And I will call that the last slide then. And I will see you in the next video. Have fun practicing. Bye-bye.